Well, we're in chapter 17 doing diodes, and diodes look something like that. If this side is positive and that side is negative compared to the other side, I would be forward biased, and my current would flow. So I could have plus 6 volts here, plus 4 volts there. That'd be perfectly okay, and I could have voltage flowing. If I'm if I'm sitting like that and I'm negative on that side compared to that side, then I'm reverse biased and no current is flowing. So my first idea of a characteristic curve for a diode would be something that looks like that, straight up in the air. And then my second approximation of the diode would be a similar thing, saying that there's a forward current voltage that I need before it turns on at 0.7 volts. So we could do that. And then my third approximation of a diode would be something that would look like this. And I'd have some knee 0.7 volts, and we call that the knee voltage. And then I'd have some breakdown voltage, and that's because if I go that negative, then, and this is 0.7 volts, the breakdown voltage is about a minus 100 volts. If I get that negative, then I'm going to destroy my diode, is basically what that's telling me. And so I have my first approximation is just a straight up and down line. A second approximation of the diode, well, there's so I need some forward voltage to turn it on. And then a more scientific approach saying that, well, there's something that happens in the breakdown region, there's something that happens at the knee, and I'm passing current through it if I'm forward biased, and if I don't, I don't. And this amount of current is very small, microamps, and I'm on a milliamp scale going up that way when I'm volts on that side. Okay, so that's what we had before. We have maximum ratings, and we have some electrical characteristics associated with our diode. And normally we don't care about those. The engineer picked a diode, we're just soldering it in, which is one way to look at it. My diodes come in all kinds of shapes, but they have one thing in common, and the thing they have in common is that they only have 2 leads. Okay, I look at this guy, where's my 2 leads? Well, one lead is the heat sink, so I'm grounding it. A for anode, K for cathode, A for and, positive. So my positive side's the anode, my negative side is the cathode, and I'm stuck with those words because that's how I did it in tube technology. So back in the 1919s and the 1920s, when I was using tubes, my tube technology also created a thing that we called a diode. It had an anode and a cathode, so those words came with us when we did it in semiconductor stuff. I've got a bar on my little guys that show me where the cathode is and where the anode is. Otherwise, like on this guy here, I'm going to have to go find the spec sheet to see who's the anode, who's the cathode. How can I tell those two guys apart? On other guys, the cathode's going to be the guy that's the biggest. So the biggest leads the cathode, the smallest leads the anode. Okay, so now we have Zener diodes, and they're diodes that are designed to operate in the reverse breakdown region. So I designed it on purpose to operate someplace where a regular diode would burn up. Can I do that? Well, I must be able to do it because I did, right? So I've got some reverse breakdown voltage going on. I have some Zener voltage on, and I use them in voltage regulation. So Well, what I mean by that, well, if I had a power supply sitting here, and I threw a Zener diode in there, and if I do the Zener diode right, and so I put in, and this is a 120 volt power supply, doing something like that. Yeah, that's what the input is. And I've got a 7 volt Zener. And I come over here and I put a voltmeter right here, and I see what it reads, and I look at it and I say, well, maybe I don't want a voltmeter. Maybe what I really want to see is something different than that. And so on the positive side of this guy, what do I see? I see that guy being forward biased, right? So a Zener diode being forward biased, nothing should happen. When I see the negative side, I see the Zener diode being reverse biased, and because it's 7 volts, I would come down to 7 volts and I would chop it off, and I would look something like that. So I'm going to be minus 7 volts on this side. I'm still going to see the 120 volts RMS on the other side, and then I'm going to repeat the situation. So my Zener diode is throwing that power, if you consider that power, sending it to ground. Okay, throwing it away. Well, how do I do that? I do that with heat, right? So the only way I'm going to do that is that I can't just ground something out. It's going to have to be heating up by Zener diode. So in this application, I'd have a huge heat sink there, so that I don't melt this thing. But that's what it would do. It would cut off the negative voltage. All right, so I'm operating in the reverse breakdown region. That's where I normally operate. If I do go forward biased, then this guy operates just like a normal diode would, but that's not why I made him to operate there. But he could operate there. That wouldn't be a problem. Forward biased is just a regular diode doing what a regular diode would do. Reverse biased, he's sitting there not burning up, designed on purpose to operate there. So I've got some current, that's Zener knee current. I've got some maximum Zener current, so I could still burn up if I passed maximum current through me, if I got above the maximum Zener current. And then I've got some test current that I test it to that is less than the maximum current that's going to burn it up. Okay, so I've got some knee current where I start going down. I have some test current that I guarantee it'll work with that much current. And then I've got some maximum current that if I get there, I guarantee it will burn to a crisp. Don't you like my guarantees? Yeah, those guarantees are guaranteed employment for electronics technicians who have to replace the Zener diodes, right? Yeah, because when the engineer puts the wrong one in. So Zener impedance, if I think about a curve that's current versus voltage, and then I think about Ohm's law, V is equal to IR. And then I rewrite Ohm's law and say I is equal to 1 over RV. And then I go back and I rethink, and I think that this is the x-axis and this is the y-axis. If I have some line going on the xy axis, I'd say y is equal to mx plus b, where b is my y-intercept and m is the slope of the line. So if I write something that says y is equal to 1 over RV, which is Ohm's law, I just wrote it a different way, and then I've got some curve associated with that. that looks like this. And I destroyed 10-minute break. 30 seconds. Anyway, so now I look at that and I say, well, this is similar to y is equal to mx plus b as I have it drawn, where b, my y-intercept, is 0, and m being the slope. So that means 1 over r is the slope. And now if I have a curve that, which is also the conductance, if anybody wanted to know that, but no one does, I know. So if I have a characteristic curve that's voltage and current, now I can just look at the change in the voltage and the change in the current, and I can come up with the impedance. So going back to where we were, if I had an AC application, I said this is 1 over RV, then my impedance would be 1 over the slope. And my slope is change in Y, change in X. So my impedance would be change in X over change in Y. Well, X is the voltage component and Y is the current component. So if I came back to my graph and said, if I go change in voltage, change in current, I can get the impedance of the operating system of the diode in that portion that is a straight line. Now, if I try to do it on a portion that's not a straight line, then I'm no longer in an algebra-based book. I'm now in a calculus-based book, and I'm doing a derivative of the function. But I'm not doing that because I'm algebra-based, so I'm keeping it simple. Okay, is that too much? There's going to be some power that's dissipated. So the maximum Zener current times the Zener voltage is going to be my power that I dissipate. So if I know the maximum DC power dissipation, I can find the maximum current allowed before this guy's going to overheat. Power derating factor. Okay, so we're gonna throw in I need 20% more so that I don't burn it up. So if I want something that's going to dissipate 100 watts, I design it at 120 watts. So I could have plus or minus 5%, plus or minus 10% tolerance of the components. Light emitting diodes, they're always fun. And a light emitting diode is going to do something slightly different. It's going to have the same characteristic curve, but it's going to need a little more current to turn on. So my light emitting diodes, if I look at the characteristic curve and I look at that knee voltage, it's going to be closer to 1.4 volts for the knee voltage. So it's going to take more than the 0.7 to turn it on. But at 0.7, with all the lights off in the room, I'm going to be able to see that it is dimly lit. It's just when I want it brightly lit that I'm going to need the 1.7 volts across it. So if I just wanted to be dimly lit, that'd be okay. Light emitting diode I could use in an application that I'd put in a regular diode as long as all the specifications are okay. When I look at my light emitting diode, I throw in 2 photon things leaving it. Well, if I don't have that, I don't come on, do I? So why we have light emitting diodes that are yellow, red, green, blue. Why are they yellow, red, green, blue?
Plastic's different color.
Because the plastic is a different color. So a light emitting diode is gonna radiate all white light, which is all the colors of the spectrum. It does not going to care, and then the color that I'm actually seeing is just the color of the plastic over the light emitting diode. Now, Here, I could have an infrared or an ultraviolet light emitting diode. Okay, so I could have the light emitting diode emit light that we can't see because of our biological imperfections, right? Some genetic problem we had 100,000 years ago when we threw away the eyesight that used to be able to see in the dark and all that other stuff, right? And so when I make those, then I'm not seeing it. The plastic has nothing to do with it being infrared or ultraviolet. That's how I made the diode itself. I have a long lead and I have a short lead, and the anode's normally the short guy, right? Oh, flat. The flat section shows us, okay, so the anode's going to be the long lead. All right. And when I try to remember, oh, that says so, cathode, the shorter lead. All right, so now I have some bright light emitting diodes that take 1.3 volts across them to turn on. And we use them in a scoreboard application. And when we use them for the math competition. And there's a seat in the room that will blind you if you're sitting in it, because these guys are so bright that they're going to get to you. So what I do is I sit in that seat, and then no one else can sit there and keep my eyes closed, take a nap. Forward voltages could be as high as 4 volts, 4.3 volts. These guys still have operating voltage, reverse breakdown voltages. They're not very big. -3 to -10. Normal diode is -100. Okay, so I lost something there. We throw in a current limiting resistor to prevent them from drawing too much current. So if I want them to have 15 milliamps of current, I throw in a current limiting resistor that would limit the amount of current going to it. So the peak allowed minus some forward voltage divided by what the operating current is going to give me that the current limiting resistor that I throw into the circuit. So when we did this last semester, our current limiting resistor for things that were real were 330 ohms. So 330 ohms is the normal real guy. So if I have 15 milliamps as the limit that I'm looking for, and I say, well, my current limiting resistor, and I've got 5 volts minus 0.7 divided by 150 milliamps, then what do I come up with? Oh, I got a calculator. Maybe I can use it. Probably not. So 5 minus 0.7 divided by 0.015, and I come up with 286 ohms, and that's not a standard. Oh, that's not a standard size. So the 330 ohm would be the standard size. That would be the one that we used. And then when we put it in multisim, the multisim light emitting diodes weren't turning on, and the reason they weren't turning on is because our regular light emitting diode turns on over a continuum of light. In multisim, the light emitting diode is either on or off. It's a digital thing. So we ended up putting 240 ohm resistors in our circuits when we build them in multisim in order to allow the light emitting diode to come on. And if I were to, I'm going to do this one more time because obviously I didn't want a 0.7 there. I wanted a 1.7, right? 1.4. Yeah, that'd be better. So I'm going to do it one more time. 5 minus 1.4 equals divided by 0.015. And I come up with 240 milliamps. Ohms, 240 ohms. But anyway, in the multisim application, we had to put in a different current limiting resistor because we don't have the continuum of the light coming on. It's either on or off. just another cross for us to bear, right? That particular formula and that particular idea will be on your next test, of course, unless it's not. It may not be, because it's a computerized test. It might be random, just to hose you over. Never can tell. So here's an application where I have a current limiting resistor preventing my diode from turning on. I could have a multicolor light emitting diode. And so we just said that the light of the light emitting diode is based on the color of the plastic, right? We just said that. And now I'm telling you that I sit there and I remove the plastic and put it on. I've got a removable plastic one and I go taking on and off. No, I'm telling you that I've got 3 different leads. So this diode will have 4 leads. 1, 2, 3 anodes and a cathode, and depending on which lead is energized will give me the color I want. In this particular case, the plastic didn't change color. Of course, I'm spending a lot for this tri-colored diode, right? This is not your 15-cent guy anymore. You're paying all of 50 cents for them, really expensive. And I can get multiple colors out of him. So I get red, or I get green, or I get yellow by going both red and green, is what that's telling me. And so, yeah, I think I have some of them. We've never used one in an application because our labs haven't called for it, but they're pretty cool. So here we go, comparison. We have rectifying diodes, we have Zener diodes, we have light emitting diodes. Silicone, germanium. I have different forward operating voltages. So if I need to be a smaller forward operating voltage, I use germanium. Reverse guy, it still operates normally in the forward direction, but I end up on purpose being in the breakdown region on the Zener diode. And I have forward operating voltages that are different, but if I ever go in the breakdown region, I'm going to get there real quick. Okay, and that's why when I test the diode to see which lead it is, I go and touch it to the 5-volt power supply and I take it off right away. Because if I left it there and I was wrong, it would burn out. Maybe I ought to try that. No, I don't think so. Right now, the yellow light emitting diodes that we use were donated to the program by General Telephone and Electric back in 2000. Some brilliant person at corporate headquarters sent out a message to the guys in Omaha to get rid of 35 sheets of inventory. And there were 35 things per sheet. And the technicians gave me a call and asked me if I wanted it. Didn't know what it was, but I said yes. And they came over with a 15-passenger cargo van filled with stuff. And so the extra stuff, we have the normal stuff that we use all the time. The extra stuff in the rooms that we have lots of all came from General Telephone and Electric. I haven't bought a light emitting diode since 2000. Before that, I'd buy 100 at a time because my budget's not all that great. But one of the line items was 1,500 yellow light emitting diodes, and so I haven't run out yet. This is we're testing the diode. So normally your voltmeter is going to have a diode testing position. So we're testing its forward and we're testing its reversed. In both cases, we're in the ohm position where 2000 K button is being pushed, and we're seeing the forward resistance and the reverse resistance. Okay, and we have a lab where we do that, and you may or may not have seen that. I'm doing it again, testing the PN diodes with a a diode tester. What did I do the time before? Oh, I'm doing a resistance check. All right, that's fine. So now I'm doing a diode check, and forward and reverse diode, what it looks like. Now I'm in the voltage position, and I have it hooked up to the diode testing position. So at 0.7 volts I turn on, and I'm seeing 3. So that would be under 10. So that would be no, that'd be 3 volts, because I'm only putting 3 volts across it. So if my voltmeter doesn't have a diode position, then I can't do the test. Yeah, I also have in the lab a characteristic curve drawer that you may want to look at sometime. That'll you can put a diode in, and it'll draw the characteristic curve for you. It does samples and things like that. The thing's older than anybody in this room, but it still works. So, testing the Zener diode. In many cases, a Zener diode cannot be tested because it was done differently. Zener can be tested by measuring the voltage across its terminal when the components are in the circuit. So normally you wouldn't test a Zener diode out of its circuit. You would have it in its circuit to see if it was doing what it was supposed to be doing. So if the voltage across the Zener diode is 0, then it's probably shorted. And if it's a 7-volt Zener diode and it has 30 volts across it, then it's probably open because you have 30 volts going into it. Testing LEDs. Well, did it come on? Did it not come on? I mean, that's how I would test an LED. Discoloration of the component. Yeah, probably. So, yeah, if I burn it up, it's going to be discolored. Yeah, that's probably what that. Current limiting for my LEDs, I'm doing the same thing. Forward operating voltage, peak thing. What's the current limiting resistor going to be? How come I'm here? Didn't I just do this? Isn't it? What I do?
You were seeing 13 before. Right?
Yeah, something happened. Testing. Oh, I'm done. There we go. So done with the presentation. Now we will proceed to figure out where we are in the problem set. And as I recall, last time we went as deep into the problem set as we could until we got to the word Zener. Okay, so problem 14, there's no Zener diode. In 1422, there's nothing there. 28, nothing there. 30. So number 30 was the first problem that used the word Zener, and as soon as we got to it, we knew we hadn't gone that far yet, and we'd had to quit. All right, so problem number 30, a Zener diode spec says the current when this guy is Zenering, what does the T mean on it? Is 20 milliamps. If the change in the impedance, the change in the current, the Zener current is 1 milliamp, and this results a change in the voltage, Zener voltage of 25 millivolts, what is the impedance? All right, so we could have remembered that formula, which we probably didn't. But so we'll go back to current, voltage, and V is equal to IR. So I is equal to 1 over RV. The slope is change in y, change in x, and it's 1 over that. So that means that I would want the change in voltage Zener over the change in current Zener. So if we remembered the formula, we'd remember that. And 25 millivolts divided by 1 milliamp gives us 25 ohms. So our impedance is going to be 25 ohms. And if I was a little bit smarter, I would have remembered that from 15 minutes ago and just wrote it down and worked the problem. But that's not the case, so I had to go back to first principles, derive the formula, figure out what it was. Where R is resistance, that's a DC component. Impedance Z is resistance, but it's an AC component. Okay, so 1 over R is the slope. Okay, so impedance would be 1 over the slope, which would be 1 over change in Y, change in X, which would be change in X, change in Y, and the change in X is my voltage, so that'd be change in voltage Zener, change in voltage current Zener. All right, so that's the thought process I went through. And if Annette was here, she would tell you how wonderful that thought process was. But that's only because, besides from you guys having to worship the ground she walks on, I do the same thing for her. And that's why she's so wonderful.
Does 1 over equal to?
What? Nothing's 1 over.
I mean, 1 over R.
Yeah, 1 over R is the slope by that equation. S-L-O-P-E, slope. Can't you see slopes?
I'm not going to make up that word.
So, well, you know, it seems like me, S-L-O-P, slope. Seems like, you know, when you get to trifocals, everything, S-L-O-P-E, slope. Whereas slope spelled differently, I don't know. Anyway, back to the next problem. 37. Well, got to turn the page. First of a different color. 37. Refer to the Zener slope spec sheet shown in 1737. 1737, I got to find a different page. Which component is rated with a Zener voltage of 8.2 volts? All right, so now I got to find 1737.
557.
I mean, it seems to me like they should have put it on the same. Okay, there we go. 550. Oh, yeah. I see the right figure. All right. So I want something with 8.2 volts. All right. So there's one with nominal 8.2. Okay, and my device would be a 1N756A. Now, do we agree with that? Yeah, looks pretty good to me. I mean, we could overthink the problem, right? And say, oh, maybe I need a design margin, right? We could overthink, and Steve would do that, and right, you know, so in a multiple choice thing, he'd pick the wrong one on purpose, just to see if I was checking his grade, his thing right, you know. So that's how that would work. So, but we could overthink the problem, but it really is that simple. We're just going to put that one. If it breaks, what are we going to do?
Put another one in?
Get a better one, right? Get something that's better than that one, right? So we might put another one in first and let it break first. Yeah, we might do that. Depends. Number 50. Now, number 50 is probably one of those thought-provoking problems that'll take the rest of the hour. Calculate, see where it says up above, pushing the envelope. I mean, that's what I do every day, right? And for Joshua today, he was working on a thing with Robert, and I on purpose put the wrong component in the picture just so he could bring it to me and complain about it. Did it probably 10 years ago. Yeah. Calculate the power being dissipated by the Zener diode in the figure below. Okay, power being dissipated. Okay, so I got some voltage. Thank you very much for not telling me what the voltage is. I've got some resistance, 820 ohms. And I've got a voltmeter about that guy. And the voltmeter says 9 volts. We'll put 9.0 to remind ourselves of something. And then we got this Zener diode over here. Well, that's really bad. Seems to me like I ought to be able to draw a Zener diode better than that. Is that better? And this is a 12 volt Zener. Okay. And we want to find the power dissipated. Well, the last time I looked, power was voltage times current. Do we know what the voltage is? Yes. Yes. Do we know what the current is? The voltage across a 12 volt Zener is going to be what? 12 volts. So we know what the voltage is because it tells us. The chances of the voltage not being 12 volts is next to none. Now, the current in the system, that's what we need. So current is voltage divided by resistance. And there's my current limiting resistor. What does it do? It limits the current. Right, so I got 9 volts divided by 820 ohms. Now it's time to take my calculator and do something. 9, turn it on, 9 divided by 820. And, well, I don't know what we'll do. We'll call it 10.98 milliamps. Okay, and then power is going to be the voltage, the Zener voltage, times the Zener current, which has to be 12 volts times 10.98 milliamps. And I've got 10 significant digits in that calculator for that guy. And I'm just going to go times 12. And I'm going to call it... well, my calculator has 0.131707317, but I only have 2 significant digits on my voltmeter. I only have 2 significant digits for everything, so I can't. My final answer can only have 2 significant digits. So that being the case, I would go final answer 130 milliwatts. So I wouldn't call it 0.130. I wouldn't call it 0.13 watts. I would change it to milliwatts and keep it that way. Well, it would appear that we're done with chapter 17, so that means we can proceed to chapter 18. Seems like a reasonable thing to do. And We can't go too far in, I would imagine. But with enough permission of everybody, we could probably get someplace, right? So there's 18. So we're going to put diodes into circuits. You know, what the heck? Why do I have diodes for if I don't put them in someplace, right? I got to use them somehow. That would be a reasonable thing. So I'm going to have rectifying circuits, and I'm going to use rectifying diodes in my rectifying circuits. Isn't that great? I'm going to have filters, and I'm going to have voltage regulators. Those are now the biggest diodes I have in the shop come from a spot welding machine. They're bigger than my fist, and they go and allow 2,000 amps to flow. Okay, so because on you want your two sides of your spot welder to come together, right? And they have huge amounts of amps to flow to melt the metal on both sides, so you have a spot weld. That's the whole purpose. So these things are designed to the wire going to them is bigger than my finger. They're designed to have 2,000 amps flow through them, which is plenty of amperage to melt some metal, right? Or your little finger, or your arm, or your entire body. Yeah, plenty. So when those guys are operating, we should try to stay away from them. Voltage regulators. Well, before Westinghouse went and built the AC generating grid, for about 10 years before that, Edison had a DC operating grid going on in the major cities. And with DC voltages, you didn't have to regulate them. You didn't have to have a voltage regulator. Then we went to AC voltage in our major cities sometime around 1890, before most of you were born. Probably not Enrique, he's probably alive then. And I know where Mundo was. I know he was alive then. Anyway, then we had to, but once we had AC power going every place, we still had to have DC power. So we had to have some way to make get our DC power back, because now it wasn't being provided by the company anymore. We had to have voltage regulators to do that. All right, so I have some input AC voltage. I'm going to rectify the voltage, and we call this half wave rectification. Well, actually, this is full wave rectification, because I'm rectifying both sides. And then I'm going to go and filter it. So there's my filter, so that it's almost straight. And then I'm going to regulate it, which gives it a straight line. So I'm using diodes in the rectifier to take the AC and making it AC only in the one direction. On the filter, what I'm doing is I'm throwing in a capacitor, which is my filter, and then I'm going to throw in a Zener diode as my voltage regulator, so that if I want 6 volts, I get 6 volts. Okay, so that's my plan. In chapter 18, that's all we do. We just do that. So I can have half-wave rectifiers, which will only give me the positive or the negative half wave of the AC. I throw the rest away. Is that a good idea? Sure. Get my efficiency right up there by throwing 50% of my electricity right out the window. Yeah. So that's not a winning thing to be doing. We don't. But I could do that if if I'm not particularly green. I don't care about the environment. I don't care how many people in China die this year of pollution or anything, right? Do I really care about that? Yeah. That's the real issue right now. China is extremely dirty when it comes to air. We were too. Not necessarily in your lifetime, But in my lifetime, our major cities were extremely polluted. And it wasn't until 1970s that we started correcting some of those problems. But I can remember growing up, pollution being a really bad idea. And now you look at it and what's the big deal? You know? But in the 20s, we were burning coal in our furnaces in our houses to heat them, and we're setting all the soot up the chimney, and very interesting time. It was much better than burning wood, because we were running out of trees. We already burned them all. Anyway, so I can take an AC signal and put one lousy diode in it, and now that I have that lousy diode in there, the positive part of the AC signal on forward bias gets passed through. The negative part of the AC signal is thrown away. It's not there anymore. So now I have a half-wave rectifier. I can put the Zener diode, I can put the diode in the other way. Now, when I'm on the positive half cycle, the guy's negatively biased. I don't see him anymore. When I'm on the negative half cycle, he's forward biased, and I do see him. So I could go either way. I could rectify it one way, or I could rectify it the other way. Now, in either event, I'm throwing away 0.7 volts of the voltage, right? Because if I put the output signal on top of the input signal, I would see that my input signal looks like this, and my output signal is 0.7 volts away from it. So I got a 0.7 volt difference between my. So I already lost some percentage of my power already because I'm dissipating it across those diodes. So I don't want to. But then I throw away the other half cycle altogether. I'm not sure that's a good idea. Maybe we can find some way to fix that. All right, so now we have to worry about this picture, because clearly it's not what we want to see, right? We want to see something better than that. All right, because clearly this picture is showing electron flow. We want it to show positive current flow. So conventional flow would be, if I'm positive there, negative there, I'm flowing that way. And then when I'm reverse biased, there's no current flow, there's no voltage across the lobe. Oh, that was nice. All right, I'm showing it backwards again, so I have to go back and do it again for the negative half cycle guy. So in the negative half cycle, my current's flowing that way, not the way in the transparency. And I'm only getting the negative half cycle of the primary voltage. It's the only thing that I'm getting. All right, so there we are. Half-wave rectifiers. I can have positive half-wave rectifiers and negative half-wave rectifiers. Sounds like something Chris would just jump on, right, Chris? Are you a negative half-wave rectifier?
No.
Or you're all positive, you're all the way? So now you can go around insulting people, you half-wave rectifier, you. And or the females, you could insult the females. Well, never mind. in one. But if you had, you know, your classmates, you negative half. So next time somebody puts a wire in your thing and it doesn't work, you just call them a negative half-wave rectifier. You know, that's why it doesn't work. Put the wire in backwards. Can you put a wire in backwards? It takes skill, right, to put a wire in backwards. Let me think. And I'm trying to think of an application where you could actually put a wire in backwards. Anybody got one? Yeah.
Fiber optic.
Oh, there we go. We could put the wire in backwards in some fiber optic, but that wouldn't be a wire. So I don't think that would count very much. Yeah, okay. I think I have one. So we have a situation where we have so here's my screw right there, and I bring one wire in this way, and I won't bring one wire in that way. Would that be putting the wire in backwards? By going in, and there's my screw, and bringing one wire in this way, one wire in that way. That wouldn't be a situation where I put the wire in backwards. All right. But that'd be a good one to accuse your lab partner of doing, right? The system isn't working, and you already know what the problem is because you figured it out yourself, and you tell them, why don't you just go take a leak, and I'll take the wire you put in backwards and turn it around, and it'll be okay. And then he comes back from the bathroom, and then it's working properly. Yeah, that'd be the way to use it. Yeah, that'd be the right application. Well, to go any further today would mean that we have gone too far because we're not supposed to go past